Have you ever wondered what makes up the universe at its most fundamental level? In the mid-20th century, physicists were on an exciting quest to answer just that. They were keen to identify the smallest indivisible particles that form the building blocks of the universe. Back then, the reigning belief was that protons, neutrons, and electrons held this esteemed title. They were seen as the elementary particles, the smallest units of matter that couldn't be divided any further. But as the scientific community delved deeper, a sense of curiosity led them to question the status quo. They began to explore the intricate dance of particle interactions and structures. They started to probe the mysteries that lay within these supposedly elementary particles. The journey was fraught with challenges, but the thirst for knowledge was insatiable. As scientists delved deeper, they began to suspect that these particles were not as elementary as they once thought. In the early 1960s, two brilliant minds independently proposed a groundbreaking concept. Meet Murray Gell-Mann and George Zweig. These two physicists, working separately, proposed the existence of a new type of particle, which would come to be known as quarks. The spark that ignited this concept was Gell-Mann's eightfold way. This was a classification scheme for particles based on symmetries. It was like a roadmap, guiding scientists towards the understanding of the makeup and interactions of particles. Gell-Mann and Zweig hypothesized that these particles, previously thought to be indivisible, had even smaller constituents. They suggested that protons and neutrons were not the ultimate building blocks of matter, but were composed of these newly proposed particles, quarks. This was a revolutionary idea. It challenged the existing understanding of matter and proposed a new layer of complexity. The eightfold way suggested a whole new world of possibilities, but the existence of quarks was still a hypothesis that needed experimental confirmation. The turning point came with a series of experiments known as deep inelastic scattering. Picture this. It's the late 1960s and you're at the Stanford Linear Accelerator Center, also known as SLAE. Scientists here are conducting groundbreaking experiments. They're firing high-energy electrons at protons and observing the results. Now, if protons were truly the smallest indivisible particles, these electrons would simply bounce off. But that's not what happened. Instead, the electrons scattered in unexpected ways, as if they were hitting tiny, point-like entities within the protons. It was perplexing, to say the least. This was the first glimpse of something more, something hidden deep within the structure of matter. It was a tantalizing hint at the existence of smaller constituents within protons, something that would later be identified as quarks. These puzzling results were the first experimental indications of the existence of quarks. Soon, the pieces of the puzzle started falling into place. As researchers at institutions like the Stanford Linear Accelerator Center gathered more data, the evidence to support the quark model became undeniable. Experiments showed that protons and neutrons were composed of smaller entities, quarks bound together by the strong nuclear force. Quarks, intriguingly, come in three flavors. There's up, down, and strange. The quark model successfully explained the properties and interactions of these particles. But there's a catch. Quarks have a peculiar feature called confinement. They're never found alone, always in combinations known as hadrons. The impact of the discovery of quarks on particle physics was monumental. It set the foundation for the Standard Model, our current understanding of the subatomic world. Today, quarks are recognized as the fundamental building blocks of protons, neutrons, and other mesons and baryons. The discovery of quarks has revolutionized our understanding of the universe, opening new frontiers in particle physics.